a pretty cool problem, and this comes from a Norwegian high school maths Olympiad. We want to find all real numbers a such that the inequality 3x squared plus y squared is at least minus ax times x plus y holds for all real numbers x and y. So we want to find the possible values of the constant a such that this inequality is true regardless of what x and y are. Do give this problem a go. Thankfully, it's actually not too bad in terms of solving this. So the way I'm going to do this is just expand everything here. So 3x squared plus y squared is at least negative ax squared minus axy. And then shoving everything onto one side, I get a plus 3x squared plus axy plus y squared. We want that to be at least 0. Now, you may have seen this before, you may not have. Firstly, notice that this inequality is very clearly true if x is 0. So if x is 0, this inequality is very clearly going to be satisfied, because if x is 0, that term will vanish, and you'll have y squared, and y squared is definitely at least 0 for every single real number y. So we can assume x is not 0, in which case I'm going to divide through by x squared. And what's the motivation to do that? Well, I'll kind of show you why in a second, but what's the giveaway that I want to do this is, well, I've got x squared, xy, y squared. So if you do see something like that, well, let me divide by x squared and you'll see what happens. So I'm going to get a plus 3 here, and then this will be a times y over x, and then this will be y over x squared. And now this is a hidden quadratic. This is a quadratic where if I just let z, let's say, equal y over x, this thing here just becomes z squared plus az plus a plus 3. And we want that to be at least 0 for any possible choice of z. And that's the trick. So this becomes a hidden quadratic, and now we're essentially just solving a quadratic inequality. So the giveaway here was that x squared, xy, and y squared, we had that. So we had to divide by x squared to turn this into this hidden quadratic. Now, you might ask, well, why do I need to check that this is at least 0 for all values of z? Well, it's kind of the fact that by making y and x certain numbers, I can make it equal any value of z. So, for example, if I wanted z to equal 3, there's a choice of y and x such that y divided by x equals 3. So z can basically be any real number. So I need to work out the values of a that make this inequality true for all values of z. Okay, how do I do this? Well, there's a few ways you can do this. I'm just going to complete the square. It's probably the easiest way to do this. So it's going to be z plus a over 2 squared minus a squared over 4 plus a plus 3. We need that to be at least 0 for all values of z. And so in particular then, that means that this part here must be at least 0. Why is that? Well, the minimum that this can be, this squared function, is when z equals negative a over 2, because here it's something squared. Anything squared must be at least 0. And so the minimum that this can be is when z plus a over 2 is 0. So when z is minus a over 2. So this thing here is at least 0. So in order to have this equal 0 for all values of z, I'm going to take the worst case scenario where z equals minus a over 2, which would mean that this guy here would have to be at least 0. And so if I kind of write that as a squared minus 4a minus 12, that has to be less than or equal to 0. So this thing has to be at least 0, and so I've just multiplied both sides by minus 4 there. And it gives me this, and now this is just a quadratic inequality, like so. So a minus 6 times a plus 2 must be less than or equal to 0, which implies that a is between minus 2 and 6. And that there would solve our problem. Pretty cool problem, not too difficult. This sort of problem I could very easily see also being in like a TMUA paper as well. Maybe not the hardest question in the TMUA, but I could easily see it being in there because it kind of uses a quadratic inequality, but you're not solving this quadratic here. You're solving an inequality with a in, but you have to first derive that inequality. Anyway, I hope you have enjoyed this video. Thanks so much for watching. I'll catch you in the next one. Have a great day.